Hi guys, I thought I would make a video to go through our next area that we'll be studying in class. The reason for this is because I know that when you guys go through the PowerPoints, it might also help to have it explained to you, and then we can spend as much time in class going through practice questions. So our next focus area will be about oxygen consumption, and this really is about meeting our needs for ATP resynthesis. So there are 5 key terms that you need to understand, and by the end of this video you need to make sure that you've got the 5 definitions written in your books and you've got some level of understanding of each. So the first term we're going to be talking about is oxygen uptake. This image shows oxygen uptake when we start to exercise. Oxygen uptake or ventilation, which has got to do with how much oxygen per litre per minute we're taking in, starts relatively low, and as we start exercising, our oxygen uptake, the amount of oxygen we're breathing in, will increase as a result. We see that ventilation increases somewhere around 75 litres per minute. This space here is showing oxygen uptake. The first term, oxygen deficit, is when O2 uptake or oxygen uptake is less than the oxygen demand to produce energy. Put simply, when we start to exercise, there is an insufficient amount of oxygen available in the body, therefore there is a deficit. There is a lag in the amount of oxygen available for exercise. The next term is steady state. O2 uptake is equal to oxygen demands. And we see here that the data has plateaued. It's stabilized. It's neither increasing or decreasing. We see here that oxygen uptake has met the demand for exercise. Put simply, when we start to exercise, yes, there will be a bit of a lag time in the amount of oxygen that's required, but eventually, if we're working at a submax pace, oxygen uptake will stabilize and it will become what's called steady. The last term is oxygen debt, and that's the volume of oxygen consumed during recovery in excess of resting levels. We also call this excess post-oxygen consumption. And you will see that this diagram will appear on numerous occasions in your exam, so it is important that you become familiar with it. The main thing that you might see in one of these pictures if it appears in an exam paper is that you'll have to identify an aspect of it. So can you identify where the oxygen deficit is? Can you identify where there's a steady state, if there is a steady state, and an oxygen debt or epoch? So we're going to go through these definitions in a little bit more detail. Oxygen deficit occurs when the demand for oxygen exceeds the supply of oxygen available. It occurs when exercise commences. What happens when O2 demands are met? Well, we see a steady state. This is when oxygen supply equals oxygen demands. Steady state. When oxygen supply meets oxygen demands. Generally, this occurs as a plateau in the data. So you can see here in the graph, there's a difference between a trained athlete and untrained athletes' acute response of their heart rate, beats per minute, and activity time in minutes. At rest, we see that there is a steady state in both athletes' data. You see that a trained athlete will start with a lower resting heart rate, which we'll learn why in later chapters. We see that a trained athlete has a lower steady state. They have a lower or smaller oxygen deficit, and their oxygen debt is not as great either. This is because they're more efficient at using oxygen. The next 2 terms that you need to understand are VO2 and VO2 max. VO2 maximum is the maximum amount of oxygen that can be taken in, transported, and utilised by the body. and this is usually per minute, or this is per minute, I should say. These three key terms are important to remember: take in, transport, and utilise. If you remember those three, you're guaranteed to remember the definition for VO2 max. VO2, however, is just the total amount of oxygen that can be taken in, transported, and utilised by the body. So, for example, I would have a VO2, okay, some level of oxygen uptake at rest. However, my VO2 maximum is when I'm working at a maximum intensity. VO2 can be expressed by two terms: relative or absolute. Relative, or a relative measure, allows comparisons between athletes of different body size. This is usually measured in mils per kilogram per minute. So, for example, if I had two athletes of different body size, I could actually understand their relative VO2 max by comparing their kilogram oxygen use per minute. All right, so per kilogram of muscle, how much oxygen are they actually consuming? The other measure is absolute, okay, and this is an oxygen consumption which just measures litres per minute, as you can see here. And you'll be able to understand which one or which measure the VO2 max is in by understanding if it's either mils per kilogram per minute, that means it's relative, or if it's litres per minute, which means that it's absolute. So what does that mean? Absolute VO2 max does not consider a person's body weight, whereas relative does. So, for example, if we had Bob, he has an absolute VO2 max of 3.8 litres per minute. And then we have Frank, he has an absolute VO2 max of 3.8 litres per minute. Now, there's no kilograms mentioned in this equation because we are not taking into consideration their weight, and this is an absolute measure. So, are they at the exact same fitness level? You might think that they are, because their measure of absolute is the same, 3.8 and 3.8. But the actual answer is no. Their fitness level would not be the same. Because Bob weighs 231 pounds, okay, which is about 150 kilos or 100 kilos. I'm not exactly sure, but he's a big guy. Frank weighs 132 pounds and he's a little guy. If we put their weight into equation, then we find out that Bob has a relative VO2 max of 36.1 mils per kilogram per minute, and Frank has a relative VO2 max of 53.3 mils per kilogram per minute. We include kilograms in this equation because we're taking weight into consideration. Frank is way healthier than Bob. He's a little guy, but he has a big aerobic capacity. Bob is a big guy with little aerobic capacity. If you only look at absolute VO2 max, then Bob and Frank appear the same. But if we look closer and we use a relative term, we can actually understand which athlete is more superior. Oxygen debt is the last term. Oxygen debt, or think about if you had a debt at the bank. This needs to be repaid. Okay, it's the temporary oxygen shortfall that needs to be repaid after exercise. While the demand of ATP decreases, we still need to repay the oxygen needed during exercise. And it's at this very end fraction where oxygen debt occurs, once exercise has stopped. And this is why we puff after intense exercise or activity. We continue to have an elevated acute response to increase oxygen intake and transportation. So even when we finish exercise, we don't see our heart rate return back to normal resting levels. This is because we've got an oxygen debt that needs to be repaid. It's dependent on intensity and duration. So the higher the intensity and the longer the oxygen debt, the longer it takes to actually repay that debt. And there is two phases. There is a fast phase, and that's where we see the restoring of PC, and that takes about 2 to 3 minutes. And then we have the slow phase of oxygen debt, and this is where we see the removal of lactic acid through the buffering process, and that's where H-positive ions are moved into the bloodstream for metabolism. We also see the restoration of regulatory functions to pre-exercise levels such as temperature. So that wraps it up, guys. I hope you found this presentation useful. You will need to go back through, pause at any point, make notes, and be ready to show those notes to me in class on Monday. Look forward to seeing you then. Thanks very much.